Welcome to the 38th lecture of Combinatorics. In the last class we were discussing the Catalan numbers and about balanced parentheses. So, if there are n pairs of brackets, right, so we saw that the number of ways to arrange them, right, balanced in a balanced way is the Catalan number, namely 1 by n plus 1 Cn 2n choose n, right, Cn n Catalan number. Now consider some n plus 1 numbers a2, a3, a4, say a n plus 1, right. Now this parenthesis may be to evaluate the product, say take some example a1, a2, a3, a4, a5. So you may multiply this together first, then you may multiply this and this together, then you may multiply this and this, then finally this and this may be multiplied. So how many pairs for 5 numbers? So 1, 2, 3, 4. So for n numbers, sorry, n plus 1 numbers, we will need n pairs of parentheses to complete the multiplication. Not that we keep this order, we don't multiply a1 with a4 in the beginning and things like that. So this the order in which the numbers a1, a2, a3, a4, a5 etc. are given is important. We don't change them, right. Just that we can start our multiplication process from anywhere in that, or in that the way it is written, right. Now you see this question also, how many ways you can multiply, this multiplication schemes, how many ways you can do this thing also will be the nth Catalan number for when we consider n plus 1 numbers, right. Why is it so? Because you know, if you consider the last parenthesis, which is always like this, so which will correspond to the multiplication of the last 2 numbers, right. So this first number in this thing may be, right, for instance we created one number here, so and then we multiply them together, this is the last one, right. So this is the nth multiplication, right. So now this, so we will have a pair of parentheses here, a pair of parentheses here, right. Now within this thing we are multiplying k numbers, say a1 to ak, and here we are multiplying ak plus 1 all the way to an plus 1, that is n plus 1 minus k numbers, right. So now if I represent by Tn or say, so to make it faster I will say that so Tn represents the number of, so the multiplication schemes when we consider n plus 1 numbers, an to n plus 1, right. Then I say this Tn can be written as, right, so the product of k equal to 0 to n minus 1, so it would be easier to, so maybe easier to understand, we'll say, I'll call it Tn plus 1 when we have n plus 1 numbers and then later change it. So Tn plus 1 is, which corresponds to this thing when we are multiplying n plus 1 numbers, right. As we have seen here, the final multiplication when you consider there are k numbers being multiplied, first k numbers being multiplied to produce one number, and the remaining n plus 1 minus k numbers being multiplied to produce the second number, and finally we are multiplying them together. But this can be done in tk ways and this can be done in Tn plus 1 minus k ways, right. So but not that k can be 1 to up to n, right. So Tn plus 1 will be equal to, I will write like this, Tn plus 1 is equal to k can be 1 to n, right. So T1 into T n plus 1, sorry, tk into tn plus 1 by k. So for instance, it first, if there is only one in the first side, then is t1 into tn. So if there are two of them, it is t2 into tn minus 1 and so on, right? Or we multiply a1 up to an first and then multiply it with an plus 1, then this is t n into t1, okay, like that. Now we will not, this recurrence seems to be the very similar to the one which we wrote for Catalan numbers. So just that we are starting from 1 to n. So for we just note that this is identical to Cn. For instance, if I write Tn plus 1 equal to Cn, right, then we can write the recurrence relation as k equal to 0 to n minus 1, right. So because this will become t0 and this will become t n plus 1 minus k minus 1, that is n tn minus k, right. Sorry, yeah, tn minus k. With n plus 1 minus k of them, we have n minus k things here. But only thing is here, see, so we have to start with, so this is the equation. So so this is like when we multiply one element, that is t1 into t, yeah, this is tn plus 1 is equal to t1 into tn plus then t2 into tn minus 1 plus up to tn into t1. But here actually there is no multiplication, we can call this as C0 and this is actually tn minus 1, right, and this can be called t1, sorry, C0, we are just reducing one, C0, sorry, C0 into Cn minus 1, and this is T2 can be called C1 and this can be called Cn minus 2 and so on. This is Cn minus 1 into C0, right. This will correspond to just Cn, right. So this is exactly the recurrence relation we had for the Catalan numbers. So we just identified that Tn plus 1 is same as Cn, right. Okay. So therefore and also the initial conditions, we will see that T1 is actually equal to C0. So T1 is, this is just no multiplication, but we can define it as 1, right. C0 is 1 and then T2 is equal to, there are two numbers, then it's again C1 is 1, right, and yeah, T3, if you look, T3 is equal to, when there are three numbers A1, A2, A3, how many ways you can do it, right. So we can do it in two ways. Why? Because either you can multiply this first and then multiply with this thing, or you can multiply A2 and A3 together and then multiply with this thing. There are two different ways of doing this. So the initial conditions are same. So therefore we see that this will give you the Catalan numbers once again, right. So it's essentially it is equal to the number of balanced parentheses, right. When n plus 1 numbers are there, we have n pairs of balanced parentheses. So why we are defining T1 equal to 0, because this recurrence relation also wants this, right. If you define T1 is equal to 0, then this is not valid, right, because we have one multiplication in corresponding to this term, right. T1 has to be equal to 1, though it is just a matter of definition, right, to get the product, right, because we are just taking A1 and then the remaining things are all multiplied together. Now if this was 0, then that term, right, how many possible ways, so that will become 0 into something that will become 0, but we need 1 as the answer, right. So sorry, right, we want Tn as the answer, right. We have this many ways and then produce it with this one multiplication, right, the final multiplication, right. So for each corresponding multiplications to produce this product, we should get 1 as the answer. So we have to have T1 is equal to 1, right. So therefore this follows exactly the same initial conditions as the Catalan numbers, just that we have to define Tn plus 1 equal to Tn Cn, and the recurrence relation is same. Therefore we get the Catalan numbers, nth Catalan numbers, as the answer to the number of multiplication schemes possible for multiplying A1 to An plus 1. Now there is another question where yeah, so this is the question. So find the number of ways to divide a convex polygonal region with n plus 2 sides into triangular regions by inserting diagonals that do not intersect the interior. So what we mean is, so you consider, say this is a polygon, right. So we can triangulate it by putting some diagonals, by inserting some diagonals, say something like this. So we can put a diagonal like this. So this got, so all are now triangular regions. This is a triangle, this is a triangle, now this is also a triangle, right. So similarly, so now let us say, so this is a polygonal region. So we can triangulate in say maybe one diagonal can be added here, another diagonal can be added here, say now another diagonal can be added here, and say another diagonal can be added here. So this is one way of triangulating this thing. So the question is, given a polygon with n sides, how many ways we can triangulate this, but not that we are putting always diagonals, right, internal diagonals, right, we don't, so this kind of things, but they don't intersect with each other. We never draw, so once you draw like this, we cannot draw something like this. This is not allowed, right. So how many ways you can do this thing? This is the question. So now of course, so we just for the ease of presentation, let's take a polygon with n plus 2 sides, right. So 2 sides. And then we will note that this is somehow similar to the problem of evaluating the expression. Suppose, so we start this is the first side, second side, third side, fourth side, fifth side, sixth side, and this is the n plus 2 side. Now I will put A1 here, A2 here, A3 here, A4 here, A5 here, A6 here, and till this will be a n plus 1. So we take this n plus 1 numbers and write like this. Now if we decide to multiply two numbers, say A3 and A4, then we can draw this diagonal here, which means that this is a multiplication of A3 into A4, right. for instance, and also if you are deciding to multiply A5 and A6, then we draw a diagonal like this, A5 and A6. Now if I want to multiply A2 with A3 and A4, I will draw a diagonal here which corresponds to A2 into A3 into A4, right. So this diagonal corresponds to that. So now see, if I draw a diagonal here, this would correspond to, or maybe I can take so this n plus 2, let's without loss of generality, this is 6 and 7, this is 8, right. Now if I draw this thing, this is A8 in A7 into A8, and now if I draw this thing, this will become A1 in this A8 is not there, so we have till here, this is not given, up to an plus 1 only we are using, this is kept blank, right. So now we can put it like this, or maybe for a change we can take this diagonal. This will correspond to A2 into A3 into A4, right. This is this diagonal into this, so into A5 into A6. So this way we can represent these multiplication schemes. For corresponding to each multiplication scheme, we will get one triangulation, right. Corresponding to each triangulation, we can get a multiplication scheme also, right. So I would let you work out these details, right, rather than wasting time drawing this thing, but I just wanted to give you the picture that corresponding to each way of multiplying, we can keep drawing the diagonals and get a triangulation in the end. Finally here we will get the entire answer, right, because here this will come, and so this into this will be copied here. So this will represent the product of A1 into this one, and this will represent the product of this into this, like that. So finally here we will get the final expression, the full parentheses, right. Indicating how we can complete the multiplication scheme. So rather than you have to work out the details of this bijection between the multiplication schemes discussed in the previous problem and this one. So not that there are n plus 2 sides. In the previous problem there are n plus 1 numbers, right. So now these n plus 1 numbers are written on the first n plus 1 side up to here, and this last one is for the final answer, right, final parenthesized expression, right. So the number of ways to triangulate a polygon of n plus 2 sides will correspond to the multiplication schemes for n plus 1 numbers, and which will essentially be Cn. So we will want to write Tn plus 2 is equal to Cn, right. This is what we want. But we can also directly see this thing, this is Cn. For instance, if you look at a polygon, and one way to write the recurrence relation is, right, see, once you triangulate and just look at this side, this has to be part of one triangle, right. It is not possible that the side is not part of any triangle after we fully triangulate this convex polygonal region, right. So you note that I haven't mentioned what is convex, because convex, see, the shapes should be similar, which formally it means that if you draw take any 2 points inside the region and draw, then that full line will be inside. For instance, if I consider this kind of a polygon, this is not convex, because if I take this point and then draw a line, this line will go outside the polygon, right. So therefore this is not convex, but this kind of polygons are convex here, right. See, whichever 2 points I take inside and draw a line between them, that will be fully inside this thing. So that's what is convex. So I thought, so you will be familiar with this concept from geometry. So now let us say coming back. So, here we have this side, and this after fully triangulating this convex region. So, this should be part of one triangle, right. Now, let us say, so what is the other endpoint of this triangle, the triangle which contains this one, right. So, the other end point can be this, it can be this, or 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 it can be this, right. There are so many possibilities. For each possibility, we will decide for typically. So, for instance, if this was the other end point, now we have got one triangular region. Now, it is clear that we can triangulate this polygon, say that this polygon, and multiply the number of ways of triangulating this polygon with the ways of triangulating this polygon, right. That will give you the number of triangulations of this polygon such that this triangle finally comes, right. So, for like that, depending on where this vertex comes, that means this other endpoint of this triangle which contains this side comes, we can get all the schemes. So, we start from here. So, when we start from here, so what happens is it will look like this. So, it will look like this, the first triangle, this is the triangle, but on this side we have a because its total number of sides is n plus 2. So, once you remove this thing, we have a polygon with n sides, sorry, n plus 1 sides, right, because 2 are removed, but 1 is added. So, T n plus 1 will be the number of ways to triangulate this portion, while after removing this thing, this side we do not have anything, but we can say that it is just a single edge polygon, that is a polygon with 2 sides. Though such a polygon does not exist, we will define a T2, the number of ways to triangulate a polygon like this. We will just say that T2 is equal to 1 to make this recurrence work, because we need the number of ways to triangulate is actually the number of ways to triangulate this portion, right. So, for corresponding to each triangulation of this thing, we can add this triangle, and we get one valid triangulation of this entire thing. So, this we will define T2 is equal to 1, right. Now, the next case is when you take the vertex to be here. So, then it will look like this. So, now this will be T, because here we have this triangle, right, this triangle. So, this triangle is T3, right, T because it is a triangle, it is a polygon with 3 sides. T3 is the number of ways to triangulate it. We know that T3 is again 1, because in a given a triangle you can only triangulate it in one way. So, there is same, namely that keeping it just like that, and on the other side we have T n plus 1 minus. So, how many will be there? So, we are, because here 1, 2, 3 are gone, but 1 is put back. So, we have Tn, right, because total. So, in this side we have 3 lost here, but 1 added. So, that means total 2 lost, Tn plus 2 minus Tn plus 2 minus 2, that means Tn. So, next will be when we allow the vertex to be here, right. So, now here we have a 4 sided triangle, that will be T4, and we have Tn minus 1 and so on, till finally we will reach to Tn plus 1 into T2 in the end, right. So, now if you, this is going to be Tn plus 2, right, but now define, suppose you identify that Tn plus 2 is equal to Cn, then we can rewrite this as Cn is equal to, this will become Cn, here Cn is equal to, the T2 will become C0, and Tn will become Tn plus 1 will become Cn minus 1, and then C1. So, T3 will become C1 and Tn will become Cn minus 2 and so on. Finally, this will become Cn minus 1 into C0, right. This is the same recurrence relation as we had for the Catalan numbers, and the initial conditions are same as we have seen, because this T2 is going to be C0 is equal to 1 as we defined it, and T3 is equal to C1 is equal to 1 as we have seen, because once you are given a polygon of 3 sides, it can be triangulated in only one way, and so the initial conditions being same, so and the recurrence relation being same, this Tn is going to be equal to our nth Catalan number, namely 1 by n plus 1 into 2n choose n. So, this is what. So, we stop the discussion of Catalan number with this last example, that is it. So, in this final problem we try to sketch out two proofs. One is to show that the basic recurrence relation, underlying recurrence relation is the same. The other thing was to get a mapping to the previous problem, namely the number of ways to put parenthesis so that we can multiply it out, right. So, it is a1 to an plus 1, right, the number of multiplication schemes keeping that order intact, right. So, but that is easy, you can just easily work out how it can be done, the bijection can be set up, right. So, these are the two methods we used to say that the number of ways to triangulate the convex polygon of n plus 2 sides is actually Cn, namely the nth Catalan number, right. So, we will go to another topic now, so namely the Stirling numbers of the second kind, right. So, we will discuss about the first kind later. So, Stirling so is for James Stirling, and yeah, this is the way we define it. So, this counts the number of partitions of a set of P elements into K indistinguishable boxes in which no box is empty. So, we have number called S of P comma K, right. So, we will have P say numbers, say 1, 2, 3. So, different objects, P different objects. We want to put them into K indistinguishable boxes. So, the boxes cannot be distinguished from each other by looking from outside, right, K of them 1, 2, 3. So, they are not labeled, okay, there are K of them, right. Now, we want to distribute these P things in these K boxes. There are two conditions. One is each box has to get at least 1. Each of these K boxes has to get at least 1. Second condition is the boxes are indistinguishable. That means we cannot tell. Suppose if you do 1, 2 here and 3, 4 here, 5, 6 here and so on, and then if I take 1, 2 from here and put it here and then 3, 4 here, that is not going to make any difference. As far as an outsider sees, it will be the same, because he sees 1 and 2 together in one box, 3 and 4 together in one box, right. So, you have to change, say for instance, if you take 3 from here and put with 1, so you make it 1, 3, and put 2 4 here, then that is different, because you will see that okay, this was different from because earlier it was 1 and 2 was always together, right, but now he does not see 1 with 2, 1 3 is coming together, right. So, it is essentially you want to decompose P into K subsets, non-empty subsets, right. In how many ways you can do this thing. This is what this count is given by SPK. So, some of the simple observations we can make about, so given a P, so let us say P is at least 1. So, there is no point about distributing 0 things into something, right. So, okay, you can, or negative things into something, we will just say if P can be 0, but let us say P is something, and then if you consider SP 0, right, if this will be, if P was equal to 0, then it is okay, we can put 1, right. If P equal to 0, we can put 1, because 0 things can be put in 0 boxes in one way. But if P was greater than 0, if P is greater than 0, then this has to be 0, because if there is at least one object and these 0 boxes, we cannot distribute them into 0 boxes, right. So, therefore, this is 0. So, SP 0 is equal to SP 0 is equal to 0 for P greater than equal to 1. SP 0 0 we will take it as 0, and another thing is SP 1. What will be SP 1? Sorry, what will be SP 1? There are P objects, and there is just one box, right. See, the point is, if P 0 or something, then we cannot put it in one box. So, that is, this has to be 0, because you know this box has to be non-empty finally, right. So, therefore, we will assume that P is greater than equal to 1. We will assume that yeah, P is greater than equal to this number, because yes, if I consider SPK where K is less than P, then if if K is greater than P, then if every box has to be non-empty, we cannot do that. So, then this will become 0, right. So, therefore, we will assume that now for whenever we consider SPK, this P is greater than equal to K, so that we can keep every box non-empty. That is one my major concern, right. So, with that condition SP1, so P1 we want to put P objects in one box, right. So, that can be done only in one way, we have to put everything in that same box, right. There is no other way to do it. Now, another thing, what about SPP? Some special cases when P equal to K, right, SPP. So, the only way is, because every box has to be non-empty, we have to give one object each to each of the boxes, because there are exactly P boxes, there are only P objects, then this has to be 1. There is only one way to do that, one object each to each box. So, we cannot see, for instance, these are these P boxes, we can put 1 here, 2 here, 3 here, 4 here. So, you may wonder why can't I put 4 here and 2 here, won't it produce a different arrangement? No, it won't, because the boxes are indistinguishable. So, whether you keep the box here or here, it does not matter, what matters is the content inside the box. So, as far as we are concerned, this 1, 2, 3, 4 is partitioned into these subsets 1, 2, 3 and 4, right. There is whether you write this subset first or this subset first is unimportant, because as far as they are concerned, so this is the way we have partitioned this thing into subset. That is only one way of doing it, right. So, that is SPP, therefore, has to be 1, right. Now what about SP2? What about SP2? Now SP2, there are P objects and there are 2 boxes. So the question is, in how many ways these P objects can be split into 2 subsets. So it's easy to see that, for instance, you try to take phi as a subset. That's not allowed because the boxes has to be so what I do is, I just, for the time being, I'll assume that this is the first, this is the second. So though the boxes are indistinguishable, so if I take phi and try to put here phi out of P, an empty set out of P, it's not allowed. So it has to be non-empty set. And not only that, we cannot take the entire P and the entire set of objects and put in this thing, because if I do that, this will remain empty. That's also not allowed, right? So this apart from these 2, any other subset of this thing can be taken, which are actually 2 raised to P minus 2 possible subsets, like that, excluding the empty set and the universe full set, right? So this many are there. If you give any of those subsets here, the remaining can be given here, then both will be non-empty. The only thing is that, so if I give an A here and say P minus A here, where A is some subset of A is some non-empty subset of P, where A is not equal to P, right? Then we are also counting this case, P minus A is here and A is here, right? But because these boxes are indistinguishable, this A being here and P minus A being here is the same as P minus A being here and A being here. So we are over counting, so we have to divide by 2, because so for every pair we are counting twice. So therefore the final answer will be 2 raised to P minus 1 minus 1. This is going to be this one, right? This many ways of doing it, right? P greater than equal to 2. This is valid for P greater than equal to 2, right? So P was 1, then we know we can't put it at all, because we cannot keep it non-empty. So that will be 0. For if you put 1 also, this will work, 2 raised to 0 minus 1. Now the next one, SP P minus 1. What about SP comma P minus 1? So we have P minus 1 boxes, P minus 1 boxes. Now P things are to be distributed here. Yeah, P minus 1 boxes are there, we have P things and we have to distribute these P things into P minus 1 boxes. How many ways we can? So you can see that because there are P minus 1 boxes, it's very clear that each box has to be empty. So we have exactly one box in which 2 objects appear, and all other boxes have just one object, right? So the kind of partitioning into subsets, this P is to be partitioned into subsets. The kind of partitions we are looking for is subsets we are looking for is 1. So P minus 2 singleton sets, P minus 2 singleton sets, and just one 2 element set. This kind of partitions. So to count this thing, it's very easy to see that we just have to decide which 2 elements go into the bigger set, right? And the remaining things can be put singleton, right? That can be done only in one way. So for each selection of these 2, then we have one valid partition, right? Partitioning of these P objects. So assignment of these P objects into boxes. So how will you decide these 2 objects? So out of P we can select in P choose two ways, these two elements. Then once you select those two elements, we put them together, and all the remaining objects we put one each into the remaining P minus 2 boxes. So therefore SP of P minus 1 is equal to P choose 2, right. So these are some of the, now this will work for right. So we will, for instance, if you are taking P equal to 1 box, so there is just one object, it should be put into 0 box, then it is 0. So here we will see that 1 choose 2 is 0. So that is correct from P greater than or equal to 1 onwards. If P is equal to 2, what happens is we have to put 2 objects into 1 box. That can be done only in one way, that is 2 choose 2 is going to be 1, right. So we can verify some initial cases, so that is all correct. And so yeah, this was some example to make you familiar with the this concept, this new concept, namely SP comma K. This is SP comma K, right. So we are putting the numbers 1, 2 up to P into K boxes, such that none of the K boxes are empty, and these boxes are indistinguishable, right. How many ways you can do, this is what it is. Now this SPK satisfy one recurrence relation. Let's look at what this is. We will take two things as initial conditions, namely SP comma P equal to 1, as we have seen before. If there are P boxes and only P things, we can only assign them to boxes in one way, right, because we are not distinguishing between the boxes. It is just that each one goes to a different box, that is the only arrangement, right. So the another condition is for SP0 is equal to 0 when P is greater than 0 and is equal to 1 if P equal to 0, right. These are the two initial conditions, we have already discussed this thing. And the recurrence relation we claim is this: SPK is equal to K times S of P minus 1 times K plus S of P minus 1 times K minus 1. So this is true for K for 1 and P minus 1. So we are not giving this recurrence relation for K equal to 0, because we have already defined it as initial condition SP0, right. This is 1 or 0 if P equal to 0, otherwise P greater than or equal to 0, this is 1, right. Similarly, we are not giving for K equal to P case, because SPP is equal to 1, this is given as an initial condition, right. So now for the remaining numbers, for when K is in between 1 and P minus 1, we are defining this, right. We are claiming that this is a recurrence relation valid for SPK. Why is this valid for SPK, right? So this is because, so what does SPK mean? SPK mean we have P numbers, say distinct objects, and we want to assign them to K boxes, these boxes being indistinguishable. So we just take the last number, namely P, we just separate it out, right, and the remaining numbers, say 1, 2, P minus 1, right. So now we will take remaining numbers are this, so we will take two cases. So some of the arrangements may have this number, last number P, as a singleton set, right. So it may have P like this, and then the remaining 1 to P minus 1 gets distributed to K minus 1 different objects. The question is, this P minus 1 things in how many ways we can distribute into k minus 1 different objects. That will count the special case, namely where this P comes as a singleton set, this comes as a singleton set. So, this is actually P minus 1 is objects are to be distributed to k minus 1 indistinguishable boxes. So, this number is S of P minus 1 k minus 1, right. So, that counts the kind of partitions where this comes as a singleton set. Now, look, this may not be the case. So, we have to, the remaining partitions are such that this P always comes with something else. So, we never have P alone. So, P may come with something more, maybe with 1 or maybe 1 and 2, or P may be coming with 3 and 4, or P may be coming with 1 and 5, so something like this, right. So, but P never comes alone. So, what we do is we just remove P and then we see k non-empty boxes again, because P was never singleton. So, when you remove P, we do not make that box empty, right. So, what we can do is to get the number of partitions. So, we can ask how many possible ways are there to put this 1 to P minus 1 into k boxes, such that no box is empty, and then put P back into the system, right. This can be done in S of P minus 1 comma k ways clearly, but now how will you put back P? P can go into any of the non-empty boxes, right, available, but there are k non-empty boxes. So, there are k possible ways to insert P, right. So, the total number of partition is this plus this. So, we get SPK is equal to SPK equal to S of P minus 1 comma k minus 1 plus k times S of P minus 1 comma k, right. So, if you have difficulty in remembering this, one thing you can observe is that if this k was not there, it is just like the recurrence relation for binomial coefficients. For instance, it will be like, it is like this. So, P choose k, binomial coefficients, right. P choose k is equal to P minus 1 choose k plus P minus 1 choose k minus 1, but here this term with k as the lower index is getting multiplied by k here, right. So, here see this corresponds to this and this corresponds to this, and then here this is getting a multiplier, that is the only difference. Otherwise, this is exactly like this. So, you can remember that. So, when you want to write the recurrence relation SPK, you can write it like the binomial one and then insert that k there. Now, think, or if you think about the proof, it is very easy. So, you just have to remember that we are partitioning it into two ways. The partitions where P comes as a singleton sets and the partitions where P never comes as a singleton set. And if P comes as a singleton set, without that we have this many possible ways of putting the remaining P minus 1 things into k minus 1 boxes, that none of them are non-empty, sorry, empty. So, and if P is always has to be with something else, then we can take P minus 1 things and put them into k different boxes, k boxes which are indistinguishable. That can be done in this way, and insert P in k ways. This is what it is. And the next thing we want to discuss, so the next thing we want to discuss is something called difference sequences. So, this we are discussing because of the reason that this is somehow connected with the Stirling numbers of the second kind, right. So, we will build up the concept first, and then we will bring out the connection. So now consider a sequence like H0, H1, H2, H3. So this is a sequence. Now we will say that the first order difference sequence for this, first order difference sequence, for this given sequence H0, H1, H2, H3 is given by delta of H0, delta of H1, delta of H2, delta of H3, and so on, where this delta of H0 is what? That is H1 minus H0. Actually we are taking the difference between this and this, that is what this delta of H0 is, and difference between this and this will be the delta of H1, H2 minus H1, right? That is what here, and this difference will be this, and this difference will be delta of H3, and so on, right? And for instance, I can consider some example. So let's consider say Hn equal to 2n square plus 3n plus 1, right? Now what would be the sequence? Put n equal to, so this sequence I will write like this: H1, H2, H3. So put n equal to 0, we will get 1. Put n equal to 1, we will get 6, right? Put n equal to 2, we will get 8 plus 6, 8 plus 6, 14 plus 1, 15, right? So if you put 4, we will get 3, so 9 into 2, 18 plus 9, 27 plus 1, 28, and so on. The next one, H4, will be equal to 45, and so you can work it out. So and we will write delta H0 here, we will write delta H1 here, we will write delta H2 here, this delta H3 here, and so on. Why? Because delta H0 is actually the gap here, the difference here, that means 5 here, 6 minus 1. Delta H1 is the difference here, that is 9, and delta H2 is this 15, so 13, and this is 45 minus 28, namely 17. This is what. Now we can define the difference sequence of this sequence, right? This 5, 9, 13, 14. That will be the second order difference sequence for Hn, because actually what is the second order? Delta square of H0. This is delta of H0. So in which case delta of H0 is 5 here. So delta of H0 is what? So this will be delta of this will be written as, because this can be written as delta of H1 minus delta of H0, which is actually this H2 minus H1 minus H1 minus H0, which is H2 minus 2H1 plus H0. But when you write the table, it is easy, because you just have to minus this from this, right? So we have written 1, 6, 15, 28 like that. So we can just write, we do not have to go to the first sequence, we can write it from the second sequence. We will write delta of square of H0 here, delta square of H1 here, delta square of H2 here, and so on. This will be 4, 9 minus 5, this will be 13 minus 9, which is 4, right? And the third one 17 minus 13, 4 and so on. Now we can define the third order difference sequence, namely delta cube of h as delta of delta square of h. That means delta of cube of h0 will be delta square of h0 minus, so delta square of delta h0, which is essentially delta square of h1 minus delta square of h0. Here 4 minus 4 0, that will be this 4 minus 0, this will be 0, this will be 0 and so on. Now we can always in this way we can define the pth order difference sequence by defining it as, see, delta p of h0 will be defined as delta of delta p minus 1 of h0, which is actually delta p minus 1 of h1 minus delta p minus 1 of h0, right. So if we keep on writing the tables, first we have h0, h1, h2, h3, h4 etc., the first sequence, which can also be written as delta 0 of h0. If you so prefer, you can write this as delta 0 of h0, delta 0 of h1, delta 0 of h2 and so on. Just define delta 0 of hi is equal to just hi, right. So there is no difference. Now here we can write delta of h0, this is delta of h1, this is delta of h2, this is delta of h3 and so on. And here we can write delta square of h0, this is delta square of h1, this is delta square of h2 and so on. This is delta square of, this is, if you take the difference between these two, we will get delta cube of h0, this delta cube of h1 and so on. So this is the concept of pth order different sequences. So we can keep on writing this different sequences. So, but we have seen that in the previous example, when we reached this is the zeroth line, where zeroth order difference equation, namely the sequence itself is written, it's a zeroth line, and this is the first line, this is the where the pth order difference sequence is written, that is the pth line, right. Here second order was written, that becomes a constant, right, second order 4 4 4 4 like that, and the third order was taken, it was already 0, everything was 0. So when we started with a polynomial, if hn was 2n square plus 3n plus 3 is a polynomial of degree 2, by the third order difference equation is becoming 0 0. What is the reason for that? In the next class we will see that if the general term is given by a polynomial of degree k, then the kth row will, k plus 1th row onwards, it will be 0. We will prove it in the next class.